Section 6.6 is Lewis structures for molecules. Lewis structures are ways of drawing or writing molecules out in a way that we can visually identify atoms and molecules, and it's a good thing for us to be able to use in chemistry, so we have an idea of what we're trying to look at in a sense. But all Lewis structures show valence electrons only, because the core electrons are not used in bonding. They're too far away from each other when two atoms come together. In order to interact and bond, it's only the valence electrons. So that's all we show. These Lewis structures have what's called bonding pairs, and it's pairs of electrons, and they're represented as two dots placed in between the two atoms that are bonded to each other. So for example, if we have sodium chloride, we could write the chemical formula as NaCl. But if we look at the periodic table, sodium is in group 1, so it has 1 valence electron. Chlorine is in group 17, so it has 7 valence electrons. Okay, so the Lewis structure for sodium would just be 1 dot. The Lewis structure for chlorine would have 7 dots. There's 2, 4, and 6. And there's your 7th dot. The bonding pairs are going to come from these two right there, and the lone pairs are shown right here on the chlorine. They're pairs of electrons that are not involved in bonding. They're represented as 2 dots placed next to each other on the outside of individual atoms. So if we were to say these two are going to react, you're going to get Na plus and Cl minus. 1, 2, 3, 4, 5, 6, and I'll have the blue ones right there. Now this is an ionic compound, maybe not the best choice as an example here, but you have these opposite charges. They can come together due to electrostatic attractions, and you get NaCl, and the 2 dots would still be placed in between them like that in a sense, but you would have to recognize these are between a nonmetal and a metal, so it must be ionic, so it's really this one up there. Now if we have, as another example, hydrogen chloride coming together. Hydrogen is in group 1. It has 1 valence electron. Chlorine is in group 7, so it has 7 valence electrons. So hydrogen redraws 1 dot, chlorine redraw with 7 dots, just like that. You have the lone pairs of chlorine right there. You've got what will become the bonding pairs in this HCl. So those are going to come together and react to form HCl like this. This is technically a crude Lewis structure. No one does this with the dots, honestly, but you could have it like that. And the more common way is to use lines for bonds, and so you could just draw this, and then your lone pairs still need to be there because chlorine needs to have 8 valence electrons. Hydrogen only needs 2. The line is the bond, and you can see it has 2 electrons in it. Single bonds are a single pair of electrons being shared between 2 atoms, as I've just showed. Double bonds are when 2 pairs of electrons are shared between 2 atoms. If we have, for example, oxygen, O2, it's in group 6. So it has 6 valence electrons. And there's 2 of them. So we have 1 oxygen atom there. And the way that you do these Lewis dot structures is I can just start right there, but you have 1, and you kind of go around in corners, 2, 3, 4. Now the next one is going to go next to that, and right there you have 2 excuse me, you have 2 lone pairs on that oxygen, and there's going to be 2 on the other. I'm going to put the 2 non-lone pairs on the right of this one and the 2 lone pairs over there. Now we're going to have those coming together, and we're going to have those coming together. And what we get when we get this reaction is 1 oxygen there. We would have an oxygen there. We've got 1, 2, 3, 4. 1, 2, 3, 4. And there's going to be 1, 2, 3, 4 electrons in between. You've got 1 and 2 pairs of electrons. And again, the more proper way to do Lewis structures is to use lines to represent the bonds. So this is how we would draw oxygen in reality. Now for triple bonds, my example is going to be nitrogen. This is in group 5. So we have 5 valence electrons, which means our nitrogens are going to be 1, 2, 3, 4. And I'm going to put the 5th one right there. You have plus another nitrogen, 1, 2, 3, 4, and 5. And so we have those 2 electrons will come together to form a bond. These 2 will come together to form a bond, as will those 2. So we get the 2 lone pairs on the outside, which I should have highlighted like that, like I've been doing. And then we've got 3 pairs in the middle, 3 bonding pairs. And you can see why I don't like this form. It's just kind of stupid. It gets, and especially with much more complicated molecules, having dots everywhere is time consuming and it's confusing when you can easily just use a triple bond like this. This picture here shows you what happens when 2 atoms of hydrogen come together. And you can see we have energy increasing up in the y-axis and the distance between the nuclei decreasing as we go to the right of the horizontal axis. So the atoms are getting closer and closer together here. Eventually they get close enough where the electron and nucleus attractions are strong, and they're stronger than you have electron-electron repulsions between the 2 atoms. So electrons from one atom repelling electrons of the other atom. You have nucleus repulsions between the 2 different atoms. And then you've got electron-nucleus attractions. When the attraction there is stronger than the sum of those, you get a bond that will form. Both hydrogen atoms need 2 electrons. They both only have 1. So what if we had this happen? What if that electron on the right just went over to there? You'd have 2 on that hydrogen, which would actually make it a negative charge, and then you'd have nothing on there, which would have a positive charge. This is a frowny face. And if the electron had gone to the right and done the same thing, you'd have H plus H minus, like that. So both of those are just not going to happen. So what happens is, since neither of those two options actually satisfied both atoms, what really happens is these atoms are going to come together. They're going to share those two electrons. You're going to get this, or really this. Both electrons exist on both atoms. So I'll say surround both bonded atoms. As you can see, you have it when that happens, you have the important thing here is that energy is increasing up. So this is the lowest energy. Things in nature tend to move towards states of lowest energy. So if it lowers its energy to form a bond, it's probably going to happen. And in the case of hydrogen, it is much less, or it has much less energy. It's much more stable to be bonded together than to be separate atoms. This table shows the elements hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine that exist as diatomic molecules. Actually, there's more elements. Sulfur exists as S6. Phosphorus exists as P4. They don't exist as individual atoms. These are the only ones out of all 118 elements that we know of that actually are polyatomic homonuclear molecules. So meaning they have the same nucleus, homonuclear, and they have polyatomic, more than one atom. Nuclear molecules. All right, so this is just another picture showing the bonding and Lewis structures of a molecule. We have fluorine molecule being formed. So it has the electrons that are to be used to share on the left, arrows pointing to them. They get shared in the middle, which you could have as a bond. And then at the end you have the space filling model right there.